Hello, I am Alberto Tufai, and I'm going to present this work, some aspects of rainbows and black hole linked to Mandelbrot's set and Farey diagram. This work was done by me, Alberto Tufai, and Adriana Pedrosa Piscaia Tufai from University of São Paulo, Brazil, and Laurie N. Gardy from Canada. This work is a sequel of our previous paper, Halo Dynamics from Rainbows to Black Holes, and was developed to the author's interest in different aspects of dynamical systems involving optics, gravitation, and the static appeal of fractal shapes. We can see here some diagrams of drops and light rays, and this is a system similar to an open billiard, and the effect of this open billiard is the formation of rainbows. Here you can see some twin rainbows, and the same can be observed for the case of massive objects like black holes bending the light from distant stars or galaxies, forming this image like this. So both are open billiards from our point of view. Well, we will present some connections between concepts of optics and Mandelbrot sets resulting from recursion formulas, feedback processes, or systems in which we have the repeated application of some mapping rule. And this is our previous work, Halo Dynamics from Rainbows to Black Hole. Let's see here, optics and event series. So here you can see multiple reflections of a laser beam in a glass plate, and you can see the sequence of events 1, 2, 1, 2, 1, 2. And this sequence of event 1, 2, 1, 2, 1, 2 reproducing this phenomenon is obtained from a circle map, that is this mapping, the plot of the, it represents the circle map in this period 2, 1, 2, 1, 2, 1, 2, 1, 2. And this is the Poincare section of this system. Let's see the circular billiard circle map in a period 3 we saw for period 2, and here we can see a period 3 using the law of reflection. So the circle map for a period 2, period 3, 1, 2, 3, 1, 2, 3, and for a cylindrical mirror we have this period 1, period point 1, point 3, point 2 is a direct mapping of this. Here we have a movie showing our experiment of this circular billiard with multiple reflections. And here we have another system, is a glass cylinder as an open billiard. And here we are observing the existence of a law of reflection and law of refraction. We have this cone of light emerging from this light scattering and project the image in a screen. You obtain the pattern. Star polygons, Farey mediant in glass cylinder, like this, and the same thing for a circular optical billiard that we show in the movie, a period 2, a period 3, and a pentagram. The combination of these two modes result in this third one due to the Farey mediant. In the open billiard of a glass cylinder, we have this Farey mediant represented in Arnold tones. This diagram represents the Arnold tones that we have period 2, period 3, period 5 between them, quasi-periodic behavior. Let's talk about the Mandelbrot set now with the star polygons, the Mandelbrot mapping. And we have a period 2, period 3, period 5, and so on. If you choose the initial conditions by this letter C. For example, a period 7 here in the Mandelbrot set is a toy model for these optical billiards. This is the main idea of this work that we are presenting. The Farey mediant and Mandelbrot set is present here, that we have regions of period 2, regions of period 3, and the Farey median between these two is this low 2/5. The Farey median between these two is this region, and the Farey median between these two is this another region. So the Farey median is present in all the parts of the Mandelbrot set, and here we have the typical zooming observation of the Mandelbrot set, in which the Farey sequence is present in all of this space. Here you can see the spiral dynamics in the glass cylinder, choosing certain values of the incident angle, and you can see this spiral dynamics in the Mandelbrot set. When you choose some initial conditions, you have this spiral in similar to this one, and this spiral similar to this one. Examples of stability of fixed points in the Mandelbrot set can be seen here for these values of the Mandelbrot set, and we have a fixed point here, intermittent behavior, another fixed point that transforms in a saddle point, and you have a period 2, period 4, and chaotic behavior, and so on. Here we have the power of the prediction of this time model, because we considered the idea of Mandelbrot hole. In the same way that you have the black hole, we used this diagram of the Mandelbrot hole to show which part here represents the situation on a ray of light is at certain angle in a glass cylinder. It can never leave because total internal reflection. And the black region at the right of the red line is an approximation of this toy model for the ray of light that cannot escape inside, from the glass cylinder, because the total internal reflection of light. So this is the Mandelbrot hole. Conclusions: multiple reflections of a laser inside the cylinder, which escapes by refraction and can be projected in screen, can be compared to trajectories of iterations of a Mandelbrot map for certain regions of the Argand plane. Based in the Farey sequence, we compared some experiments in optics with Mandelbrot set. The open optical billiard is an approximation of a light ray traveling in a drop, like the case of rainbows. Considering the ray of light in a cylinder, there are some trajectories that do not escape from the cylinder, like the case of light in a black hole, due to total internal reflection. We thank to these people and these research agencies. You can see some of our references here. And thank you.